Hello everyone, welcome to Recitation session week 6 for CEE222 Water Resources Engineering. This week we will have 6 similar questions and let's get started with the first one. The first question is 5.5.3. In this question, as you can see in the figure, we have a pump which delivers water from reservoir A, which is here, to reservoir B, which is here. And the pipeline has a length of 1,650 meters and diameter is 0.5 meters. And the Darcy-Weisbach friction factor is 0.018. And in this question, we are ignoring minor losses and we need to determine the flow rate and the velocity in the pipeline. And in the table, we have pump characteristics. First of all, let me write elevation of these reservoirs, which is 47.5 and 55.9 meters. So in this question, we need to find the flow rate and the velocity. And differently from previous questions, we are given pump characteristics. And here you can see the pump as marked as P. So as always, let me get started with the energy equation between these two reservoirs, reservoir A and B. So we have HA elevation, velocity hat, pressure hat, and since we have a pump here, we will see the impact of pump. So let me write HB. This is equal to HB plus velocity hat for surface B, reservoir B, pressure hat, and finally the head loss, of course. And since we are ignoring the minor losses, I directly wrote as HF, which is frictional head loss. Let me simplify this. So we will have HA. And since this is reservoir and it is open to atmosphere, we can eliminate PA, VA, VB, and PB. So it gives HA plus HB is equal to HP plus HF, which is frictional head loss. And from here, if we leave HB alone, we will get HB minus HA plus HF. And let me write this as HS, which is the elevation rise. So it is elevation rise because the elevation was 47.5 meters for reservoir A, and we are rising the elevation to 55.9. And here HP will be the required pump head. So we also have frictional head loss. So we need we need a pump head that should cover this elevation rise and also head loss. So when we calculate the head pump head, it will be sum of these two values. So here we will change the donation of HB, the name of HB. So let me write here instead of HP, let me use HS, which is system at, is equal to HS plus HF. We are doing that because the right-hand side of this equation can be computed for various flow rates. Therefore, we can refer this value as system at. So it is now the system at. So when we say system head, it will be actually the relationship between, when we say system head curve, it is actually the relationship between H has H and Q. So you will see that in this graph. So here we have a system head curve, and it is the relationship between HSH and Q. So you will see the difference between HSH and HB. So here, the main objective is to determine the actual flow rate in the pipeline with the existing pump, which was here. And we need to determine the actual flow rate, not to determine hypothetical pump heads required for different flow rates. So to determine the actual flow rate, we superimpose a plot of existing pump characteristic curve, which you can see here. And it's actually coming from this table. So here we have a relationship between Q and HB. And here, this blue curve is representing this relationship, which is HB and Q. So we will also have a system curve, and the intersection of these two curves represent the flow rate of that particular pump operating in this system. So that we have this variable as system head, and we can continue with the calculations, and you will understand it better, actually. So from a table 3.4, as you know, we had a head loss, which is equal to K times Q to the power of M. And since this is British system, since this is SI system, we are going to use this one. And since that's VISPA, we need to stick with this row. So the M will be 2, and we will need to use this equation to calculate K. So from the table, HF is equal to K times Q to the power of M. And from the same table, K is 0.0826 FL, or e to the power of fifth, and M is equal to 2. If we use F as 0.018 and L as 1650, we will get K value as 78.5. So here we need a spreadsheet because we are going to find different frictional losses for all of these Q and HP values. And finally, we will also get the system head values, so that instead of doing everything manually, you can use a spreadsheet. Actually, we have a simple one here. So let me summarize this table and let me write sheet. Okay, so these two columns are coming from the table from the question. So we had relationship between Q and HB. And after that, we can calculate HF using this equation. So since we calculated K as 78.5, for example, we have Q here and we know the M. So since Q is 0, we will have 0 head loss. And for example, for 0.15, we will get 1.8. Actually, let me show, for example, this one. So HF will be equal to 78.5 times 0.15 power of 2. So from here, HF is equal to 1.8 meters. So when we do all of these calculations for each row, you will get the frictional loss. Since we ignored minor loss, these are all 0. And HS was the elevation rise from A to B, and it is a constant because we have constant water surfaces. So they are 8.4 meters. So now, based on these values, we have system hat, which we used here in the energy equation instead of HV, because we need to find the actual rate, actual flow rate, and to find this actual flow rate, we need to find the intersection of HP and HSH. So we need to intersect pump head and the system head, and it will give the actual flow rate in this system. So after we do all of these calculations, we will get this table. And you can just basically use a spreadsheet or Excel. It will give the results in seconds. So for example, for the first system head, we are going to sum HF plus HS, which will give 8.4 meters. And it is actually coming from this equation. So again, with the same equation, for example, let's calculate this one. We calculate head loss as 15.9 and HS is constant 8.4 meters, and it gives 24.3. And finally, let's calculate this highlighted one. So the head loss is calculated as 44.2, and the elevation rise is 8.4 meters, which gives 52.6 meters. And as you can see, it is the same with the HP. So this actually means that we have the same pump head as the system head. So this is the actual flow rate for this system. So let me write actual Q. So others are hypothetical, but this is actual one. And we can also see that in this figure, in this graph. And this is pump characteristics and system head curves graph. So first of all, we actually knew that this is the pump curve, and it is coming from Q and HP relationship here. After that, we have system head curve for all of these Q values. And it is clear that they are intersected they intersected here, and this will be the actual flow rate, which is 0.75 cubic meter per second. And the corresponding pump head will be the required pump head in this system. So in the question, we need to find the flow rate and the velocity. And since we already calculated the flow rate as 0.75 cubic meter per second, we can directly calculate flow rate as a velocity. So it will be 0.75 meter per second over area p times diameter over 4. And it gives 0.82 meter per second. So this is the velocity, and this is the flow rate. Let's continue with question 2, which is 557. Here again, we have a transmission system with a pump. So we have the elevation of HA and HT. And the friction factor is 0.02 for all the pipes. Pipe AB is 4,000 feet long with a diameter of 3 feet. Pipe CD is 1,150 feet long with a diameter of 3 feet. The branch BC has a length of 100 feet and a diameter of 2 feet. So this is BC1. Sorry. And uh, we have branch BC2 as 500 feet long and a diameter of 1 feet. And this is branch 2. Again, we have pump characteristics, and we need to find the system flow rate, pump head, and the discharge in both of these branches. So I already marked all of these information on the figure. So let's continue with the calculation. So first of all, if you may remember from previous recitations, when we have parallel pipe, we were using equivalent pipe equation, which is equation 3.47 in your textbook. And we were choosing some values for diameter and friction factor. And if you remember, I mentioned that it is arbitrary, so you can choose any close values to other pipes. Of course, the values you choose shouldn't be so crazy, but something close. So let's say diameter is 3 feet, because we have 3, we have 1, 2, so 3 should be fair. And for the friction factor, let's say 0.02, because actually it is same for all pipes, so it is better to continue with the same value. So from the equivalent pipe equation, let me write it here. We have d to the 5 Fe Le as root square. So we are using d1 plus same for d2. So this is give this is giving 3 to the power of 5, 0.02 LE is equal to this time 2, which is coming from here. And we are going to use L1. So the friction factor is same times 100 feet plus this time branch 2 with a 500 feet long and 1 feet diameter. So 1 to the power of 5, 0.02 times 500. And this gives, let's write it here, LE is equal to 652 feet. So let's assume that we created an equivalent pipe here, and it is 652 feet. So actually we can find an equivalent pipe for the entire system. So it is basically the sum of all of these pipes. So let's say total length, we had 4,652 plus 1,142. This gives 5,792 feet as the entire length. So similar to the previous question, we can create a spreadsheet. So we are going to use same things, but this time, since we are dealing with British system, we need to use this equation. And for the head loss equations, we are going to use the same one, which is k times q to the power of m. So let me use this equation and find the k value. So k is 0.0250 times f l over d to the power of 5. Actually, let me check if it is correct. Yes. From here, we will get f is 0.02. The total length is the value we already found. And diameter is 3 to the power of 5. It is 3 because we assume that a diameter has 3 feet for this equivalent pipe, and so that we have the same diameter for the entire pipe. This is giving 0.012. Okay, now let's get back to the spreadsheet. Similar to the previous question, the Q and HP columns are given here, except this value because it is an interpolated value between 10 cubic feet per second and 20. So as we already did in the previous question, we are going to use HF is equal to K and Q to the power of 2. So for 0, of course, it will be 0 head loss, and we ignored minor losses. HS, which was elevation rise, and it is 50 feet because it is the difference between HD and HA, and it is constant. So if we do all of these calculations, so we need to find actually HF for all of these Q values. So after we found all of these friction losses, we can get the HSH, because if you remember the equation from the first question, HSH is equal to HS plus HF. So for example, for the second one, we have 1.2 and 50, which is equal to 51.2. And for this one, you have 54.8. But as you can see, they are not equal yet. For example, it is 51.2, but we have pump head as 55. And for 20 CFS, we have 47 feet HP, and we have 54.8 HSH. So here we can create the table similar to the previous question. For example, 7, 23, 47, 47, 55, and 60. I know it doesn't look very cool, but let's continue with this one. So we have 0, we have 10, we have 20, 30, 40, and 50. These are Q values as CFS, and these are HP values as feet. Okay, so let me mark points. So we will start with this one, because for 0 we have 60, for 10 we have 55, and let's continue with all of the points. For 30 we have 37, for 40 it is 23, and then we have this. So if we draw this line, this curve, we will have something like this. And then let me create a system hat. We are going to create something like this one. So let me move this here. So for the HSH, it's starting from 50. Let's say it's something like here. And we have 51.2. And we have 54.8, like that. Okay. For now, let's stick with this. And it is 50 when we have 0 CFS, and when we have 10, it is 51.2. So it will be something here. And when we have 20, this time we will have something like 54.8. So it should be around here. When we draw the curve, we will have something like that. So it needs to go higher because we have higher values, even higher than 60. So intersection should be around here, so that we need to make some predictions to get that. And since it is here, we can say that it is between this point and this point. So this point is 55 HP, and this point is for 47 HP, 47 feet. So this actually says that we will have a value between these two curves. So we need to make some predictions, as I mentioned. So you can use your calculators to find these interpolated values. So when you try, for example, you can start with 15. And for 15, you will have a head loss here. And based on this head loss, you will have HSH, which is system head. When you see it is not the same with this HP, and then you will need to increase or decrease your value. So basically, based on the solution, if we use 13.5 CFS, it gives 52.2 feet HP. And this is giving system head as 52.2, which is the same with HP. So that this means that we can stop here and we can take our flow rate as 13.5 feet. So this is the intersection, and we get it from interpolation between two points. And these 2 points are actually between 10 and 20. And also, since it is close to 10, we can start, as I mentioned, like 15, then we can go back. So the intersection gives 13.5 CFS. Okay, now we have found the pump rate, sorry, pump head, and we found the system flow rate as 13.5. Then we need to find the discharge in branches 1 and 2. And this is, of course, much easier. So let me use yellow. So we need to find the discharge. So we can start with head loss, because head loss is actually K times Q to the power of M. So that here we will get, using this equation, we will get 0.0252 times 0.02 and 652, which we found here as the equivalent length. And now actually we are calculating this one, which is equivalent pipe. Then we will skip to the branch, and the flow rate was 13.5, and we have M over e to the power of 5, which is 3 to the 5. This gives 0.246 feet. And now we can calculate head losses for each branch. And if you remember from previous lectures and recitations, head loss 1 here will be equal to head loss 2. So this means that we are going to use the same head loss, same friction head loss. So 0.246 is equal to, actually, let me write it to the next page. So HF BC was 0.246 feet, and this is equal for first branch and for the second branch. So let's continue with the first branch. The length was 100 feet, and we will have Q1 square, and the diameter was 2 for the branch 1. And for the second one, we will have 500 feet long and 1 feet diameter. So E2 is equal to, sorry, this is actually this is K. So the formula was HF is equal to K QM, and M was 2. So this is coming from this equation. M Q2, and this diameter was 1. And from there, you can get Q1 as 12.5, and Q2 is 1 CFS, because the total flow rate was 13.5 TFS. And since the flow rate is moving, the water is flowing from here to here, from A to B, it will be same through the pipe. So this gives the flow rate in each pipes. Okay, question 3, 562. Here we have 1.5 diameter pipeline, and it conveys water from reservoir A to B. So here we have reservoir A and B. The pipeline is 13,800 feet long, and the vice friction factor is 0.02. Water surface in reservoir B is 196 feet higher than that of A. So it actually means that we have an elevation raise as 196 feet, which is HS. We are neglecting minor losses, and we need to find the flow rate and energy head added the flow by each pump. So this is different from the second and first question. And if we use 2 identical pumps in series. So here, let me draw that. Let's say this is pump 1. And let's say we have another pump. It is pump 2. And again, we have pump characteristics as given in this table. Okay, if I remember the equation, we had system head HSH as equal to HS plus HF. And for HF, we had K, Q to the power of M. And since this is British units, we will use 0.0 to 52 FL over D to the 5. And here, since we have two pumps, the heads are doubled. Or two identical pumps. It is doubled because these are identical pumps. So we will have double head. And let me calculate K value. So it is 0.0250. F was 0.02. The length and diameter 1.5. This gives 0.916. Okay. So here again, we have the spreadsheet. And in the question, we had pump characteristics as the relationship between Q and HP. So we have these Q values and we have these HP values. So if you pay attention here, for 0, we had 300 feet. But since we have two identical pumps, this time we will have 600 feet as pump heads. And it will be the same for others as well. For example, for one pump, we have 289, but this time we have 578. And for example, for 25 CFS, we had 25 pump heads, 25 feet. And since we have 2 HP, 2 pumps, it is now 50 feet. And let me, for example, calculate this one. As we always do, HF is equal to K, Q, M, which is actually 2. And 0.916 times 5. Let me verify this equation calculation. So we have 9. Yes, it gives 22.9 feet as the head loss. So again, you can use the spreadsheet and you can use this formula to calculate all of these values. And again, we have a constant elevation raise between A and B. So the total system head will be sum of this HF and HS based on this equation. Okay, so once we calculate all of these equations, all of these values, we will see that at 15 CFS, we have 2 HP as 402 feet pump head, and system head is also 102.1. Since these are very close to each other, we can accept this value as our actual flow rate. And if we also look at the table, so we will have this pump heads, which is double of the pump head given in the table. And we have the system head, and as you can see here, we have the intersection for these two curves. And based on this curve, we have 15 CFS as actual flow rate, and HP is 402 feet. So as I mentioned, these are very close to each other, so we are accepting the pump head as 402 feet. And in the question, we are asked to find the flow rate and the energy head added to the flow by each pump. So this is actually coming, this pump head is actually for two pumps. And since we need to find the single pump head, it is almost 201 feet for the first pump, and it is same for the second pump. And the flow rate was 15 CFS. Okay, question 4, which is 565 in your textbook. So here again, we have a pump pipeline system, and it delivers water from reservoir A to B. The HA is 45.5 and HP is 92.9 meters. The pipe has a length of 1,860 meters, and its diameter is 0.5 meter. And thus the vice friction factor is 0.02. And this time we are considering minor losses, including inlet, exit, and swing type check valve. And again, we can see the pump characteristics in the table below. Here, when a single pump is used in the pipeline, the flow rate is 0.5 cubic meter per second with a pump head of 73 meters. So when a single pump is used, the flow rate is 0.5 and the pump head is 73 meters. Now we need to determine the flow rate in the pipeline if two identical pumps are used in a parallel combination. Also determine the flow rate in the pipeline if two identical pumps are used in a series combination. So the question says that we need to use a parallel pump system and also a series pump system. So actually we did series in the previous question. So when we have pumps in series, we were doubling the pump head. And this time when we have pumps in parallel, this time we are doubling the Q for each value of HP. And this is of course for each Q. And using the equation from previous questions, this one, which is the system head equation, we can get started. So we had system head equal to HS plus head losses. And this time we have frictional head loss and also minor head losses. HS, which is the elevation rise from A to B, is 47.4 meters, which is distance, which is the difference from 92.9 to 45.5. And for HF, we are again using KQ to the M. And for HM, which is the minor loss, we are using total loss coefficients times V square over 2G. So for the friction loss, let's calculate K value. Again, we need to refer to the first question. So we are using SI system. So we are going to use this value, this equation, which is 0.0826 FL. Yes, it's here. F is 0.02, L is 1860, and diameter is 0.5 to the 5. And this is giving 98.3. So for minor losses, we are going to use loss coefficients. So KE, which is the entrance, which is entrance is 0.5. We have loss coefficient for the valve, which is 2.5. And finally, we have KD, which is the discharge or exit from the pipe, and it is 1. So in total, it makes 4V square over 2G. And we have velocity. So currently, we don't know velocity because we need to find the minor loss for each of these flow rates. So let's continue with this table. Actually, let me make closer them. Okay. So let's start with the series pumps in series. So as we mentioned, we are doubling the pump head. So if we check the table, for example, it was 91.4. Now it is 182.8. And we are doubling all of these pump heads. So for friction head, we are going to use K times Q to the power of 2. So K is 98.3. So we can calculate all of these values based on this equation. And for minor loss, we had 4V square over 2G. So for example, let's make a calculation for 0.15. Here, Q is 0.15 cubic meter per second, and the velocity will be 0.15 over area. Diameter was 0.5 over 4. And from here, we will get 0.76 meter per second. And then when we use this value in minor loss, this time we are going to get minor loss, we get 0.11 meter, which is written here. And you can do the same for all of these pipes, all of these flow rates. So basically, you will have different flow rate, different velocities for each of these flow rates. And after that, using this minor loss equation, we are going to get these minor losses. Okay. So now we have frictional loss, we have minor losses, we have HS, which is the difference between elevation of B and A, which is constant. So using this equation again, the system head is equal to HS plus head losses, total head loss. So for example, for again 15, 0.15, we have this HP value 179.6. We have 2.2 and we have 0.1 head loss, and we have this HS. So okay, so the total system head is 49.7 if we sum all of these values, which is HS plus total head loss. And we see that it is not equal to HP. So we need to find similar or equal values, which is coming when we have flow rate of 0.75. So here, first of all, we are calculating velocity based on this flow rate. This flow rate is normally giving 52.6 HP, but since we doubled pump heads, it is now 105 and 2. And using kq to the power of m, we can get 55.3 head loss, which is friction head loss. And again, using for v square over 3g equation, we can get this minor loss. And we had elevation rise. So the sum of these three values is actually 105.7, which is very close to pump head. So we say that there is an intersection here, which is intersection of pump characteristics and system head curve. So for this question, for this pump, the actual flow rate is 0.75 cubic meter per second. Now we can skip to the parallel pipe. So when we have parallel pipe, as we mentioned here, this time we are doubling Q for each value of HP. So as you can see, we had 0, 0, 15, 30, 45, 60, and now we doubled all of them, and we have 0.30, 60, 90, and it is going until 1.80. However, we keep HP values fixed, so 91.4, 89.8, they are all same here. And actually, let me highlight this. For series pipe, we doubled HP. For parallel pipe pump, we doubled flow rates. The remaining calculations are same. So again, we are using KQ to the power of M. And for the minor loss, again, we have for v square over 2g. And of course, these are 0. And when we have 0.660 flow rate, so actually when we have 0.30 flow rate, which is double tier, and it is now 0.60. And the value for that flow rate is 85.1. And don't get confused about this value and this one here. Since we doubled flow rates, we actually need to use this HP because we doubled this one. We didn't get this value. So when we double it, it is now 0.60, and the HP is 85.1. We calculated friction head loss, we calculated the minor loss, and this is of course constant. And finally, this gives 84.7, and we had 85.1. So we say that these are again very close to each other. So we can get this flow rate as the actual one. So when we have two pump series, Q is 0.75 and HP is 150 meters. When we have two pump in parallel, the flow rate is 0.60 cubic meter per second and HP is almost 85 meters. Okay, question 5.7.3. Here we have a pipeline pump system, as you can see in the figure. And this time we have three reservoir system. And each pipe has the following properties. Diameter is 1 meter, length is 1,600 meter, and F is 0.02. And actually there's a typo here. So you should take diameter as 1 meter, length as 2,000 meters, and F is same, 0.02. So make this correction. Length is 2,000 meters. Okay. And again, we have two pumps which are identical. And in the table, we can see the pump characteristics. The water surface elevation in reservoir A is 26.2 meters, and in the reservoir is 33.5 meters. The discharge in pipe BC is 500 liters per second in the direction from B to C. So we need to find three different results. The first one is discharge in AB and BD. So discharge in this pipe and in this pipe. Water surface elevation in reservoir C, and the head added to the flow by each pump. And it will be option C. Okay. So let's write what we know so far. So actually we can divide all of these flow rate values by 1000 because they are given in liter per second. So to divide it, to find in cubic meter per second, we need to divide everything by 1000. So we can get cubic meter per second. So QBC is 5000 liter per second, which is actually 0.5 cubic meter per second. So we have QBC as 0.5 cubic meters per second. And the flow is from B to C, and also from B to D, because we are using a pump to move water from reservoir A to D. And for D, it is 33.5 meters, and the elevation of A is 26.2. So here we can see that QA is equal to QB plus QC. Actually, QBC plus QBD, and let's say this is QAB. So the QBC is 0.5 cubic meter per second, Okay. Now in this system, we need to use a spreadsheet because in the system from A to D, we only have one pump, which can help us to find the flow rate in AB. We will be doing the same thing that we did in previous questions, so that we can find the actual flow rate for this using these two pipes. And we only have one single pump. And if this pump, the second pump, even if it was here, nothing will change. So we were going to behave like pump in series, like question 3 and 4. So we were doing the same calculations. So let's get started with the calculations. Since we already know the flow rate in QBs in pipe BC, we are writing equation from A to D. So we will do our processing on these pipes. So as you know, we need to find head loss at AB and head loss at BD. Because to find the actual flow rate, we need to find the system head, and the system head is coming from the elevation rise plus total head loss. And in this question, we don't have any minor loss. So we will be considering friction losses in pipe AB and pipe BD. So the equation was HF is equal to KQ to the power of M. And since we are using SI units, let's check it. We're going to use this one again. F is 0.02 times 2000 over diameter is 1, which gives 0.30 meters. And this will be same for the second pipe because it also has same properties like diameter, length, and friction factor. They are all same. But if they were different, of course, we needed to calculate K value for this pipe and this pipe separately. So actually, this is K. Okay, now we have K value. And here we also know that QBD is equal to QAB minus 0.5 cubic meter per second, which is coming from this equation. And when we are calculating the flow head loss, we need to use this flow rate. So head loss BD will be based on QBD, which is QAB minus 0.5. Okay, so actually we can create a new column here, which is QBD. And since it is QAB minus 0.5, we will not have any value because we cannot have negative flow rate. And this is also negative, so we are not using them. But here we will have 0. So this is QAB. This is 0.25. This is 0.5. This is 0.75. And finally, 1. As always, we have these values from the table. And this is these are pump characteristics. And using the equation k q to the power of m, we can calculate head loss in pipe AB. So as we always do, we can get these head losses using k and q from this table. So these are head losses in pipe AB for corresponding flow rates. And for BD, since we didn't have any value, we are skipping this, and we will directly start from flow rate 0. For flow rate 0, we have 0 head loss. And for flow rate 0.25, we have 0.2, so that we will have the same one here. So basically, we are shifting these head losses to here. As you can see, it has same values. So actually, there's another typo here. In the question, it says the elevation of reservoir D is 32.5, but it is actually 35.1 meters. So you need to also fix that. So let me write that. So based on this value, we can calculate the elevation rise, which is 35.1 minus 26.2, which gives 8.9 meters. And again, using this equation, we can get the total, we can get system head. So it is the elevation rise plus total head loss. So for example, if we look at 0.75, we have 8.9 meters, and we have these two head losses, which gives 11 meters. And since we need to find same values for the pump head and for the system head, we can see at 1 cubic meter per second, we have the same. We have the same pump head and system head, which is 13 meters. So that we say that the actual flow rate is 1 cubic meter per second. And of course, this is in pipe AB. So let me write that here. Since it QAB is 1 cubic meter per second, QBD will be equal to 0.5 cubic meter per second. Now we need to write energy equations. So let me open another page. Currently, we know all flow rates in AB, BD, and BC. So let's check what we have found. So in A, it says discharge in AB and BD, which we already calculated. So we can skip to the B. So in B, we need to find water surface elevation in reservoir C. So let's keep going. We have A to B and B to C, so that we can start from energy equation between A and B. We have elevation of A, and we have pump at HB at AB, and this will be equal to AB plus head loss AB. So we basically write an energy equation between A and B. So we have elevation here, we have elevation B, we have pump, and we have frictional loss throughout the pipe. So to find the elevation of B, elevation at A is 26.2, and the pump head is 13 meters, which we get here, equal to EB plus head loss. And head loss is coming from K Q to the power of M, and K is 3.3 times Q. Flow rate was 1, so we directly write 1 here. From here, elevation at B will be 35.9. Okay, now we calculated elevation of B, which is 35.9 meters. And the only remaining is the elevation at C. So we need to write another energy equation between B and C. So let me write that. Energy B to C. So we have HB plus H pump equal to, we have HC plus total head loss on that pipe. And actually let me write BC instead of B to make it clear. So this is head loss throughout the pipe BC, and this is the pump BC, because as you can see we have a pump which is between B and C pipe, B and C points. So here we need to check the table because we need to find the pump head. So in the question it was given that the flow rate in BC pipe is 0.5 cubic meter per second. And if we have this flow rate, this means that the pump head will be 19 meters for this pump, based on this relationship. So let me use that here, which is 19 meters. We had elevation of B, which is 35.9 meters. And then it will be equal to HC plus the total head loss. And if you remember, total head loss is K times Q to the power of M. K was 3.3 times, and the Q is 0.5 cubic meters per second, QBC. And let's use that here. And from here we will get HC as Let me quickly calculate it. So we have 35.9 plus 19. And if we send this to the left hand side, which is the head loss, we will get 0.5. We will get, sorry, 54.075 meters as the elevation of sea. And let's see what we need to find. So water surface elevation in reservoir C, and we already found that as 15.075 meters. Question 6. And here we are going to determine the discharge in each pipe in this figure. And we have elevation of A, B, and C as 180 and 120 feet. And in this table, we have pipe and pump characteristics. So here we have two pumps in pipe 1, and we have another pump in pipe 2. So basically, we have two total pumps. So from the figure, it is obvious that this pump will pump water from A to this point, and this pump in pipe 2 will pump water from reservoir B. So this means that these flows will merge at this point, and they are going to flow into reservoir C. So this will be the first equation from this image. So here I need to talk about some facts about pumps and their energy. So here the pump 1, say pump 1, will use its energy to overcome losses in this pipe. And similarly for pump 2, it is going to use its energy to overcome friction losses throughout this pipe. So that instead of this given pump heads, we need to find net pump head. Because these two pumps have used their energy to overcome losses in sending flow through pipes 1 and pipes 2, and then raising the water to higher elevation, so that their total energy is not available to overcome the friction losses in pipe 3. This means that we will have a net pump head which is lower than these two columns. So you will see what I'm talking about in the next page. Before that, let me summarize what we have so far. So we have length, diameter, and friction factors for each pipeline, and these are given in the question. So you can check them out. So we can just put this mark because we already know everything. Apart from that, as we always do, we are going to use head loss equation. And since these are a British unit, we are going to use K as 0.0252 FL over D to the power of 5. And since each pipeline has different length, time, and diameter, we are going to find different K values. But of course, the M value will be the same because we are using Darcy-Weisbach equation, and it is constant as 2. And these are the reservoir data, which are elevation for each water surface elevation. Okay, and now we can talk about the net pump heads. Here you will see these two terms. And let me summarize that. We are doing that because we are using this. We are using the energy of these pumps to overcome losses through this pipe for pipe one, using pump one, using pump one to overcome losses in pipe one. Sorry, and we are using energy of pump two to overcome losses in pipe two. After that, they will lose their energy, and then eventually we will have reduced pump heads for each pump. So let me write what was given, and this two is given in the question, and this one also given. So these are characteristics, pump characteristics. However, we are going to reduce them. So for example, to find the net pump head for the first pump, we will do this calculation. Let me write it here. So we have we already have pump one or pump head for pump one. Then we are going to have head loss through pipe one, which is here. And after that, since as I mentioned, we used the energy, there will be an elevation difference between these 2 points. So that we also need to consider this elevation raise, which is 20 feet from A to C. So yes, so we are going to subtract this value as well. Let me say HS A to C. So for the second pump, this time we have HP2, of course. We have head loss 2 in the second pipe. And also we have elevation from B to C, which will be 40 feet. Okay, for example, for the pump one, let me calculate for the second row. So the actual pump characteristic is 195, the actual pump head for this first pump. However, it needs to overcome the head loss in pipe one, which is HF1, minus we will have 20 feet from A to C. So actually, let me get started with the first one. So here we have HP1 as 200 and net HP1 is 180 because if you remember, we have this head loss equation, and since the flow rate is 0 here, we will have a 0 head loss. For example, if we have this type of column, we have 0 head loss. This means that we have 200 for the first row, we have 0 head loss, and we have 20 feet elevation. So this elevation and head loss is reducing the pump head. So finally, we will get 180. And for example, for the second one, let's say again, we have 195. And this time we need to calculate the head loss. So for example, for here, we are going to use this K value because it is pipe 1. So let me do it here. We will have this value times the flow rate to the power of 2. So let me quickly calculate this value. So we have 0.1250 times the flow rate is 10 to the power of 2. So this is giving 12.5 feet head loss. So we had 12.5 and we had 20. So it makes 32.5. Finally, it makes 162.5. Similarly, for second pump, we are going to do same calculations. And this time we are going to use this K value, which is 0.1406. And using this equation, we will get the net pump head for pump 2, which will be here. Okay, now we calculated all net pump heads for these 2 pumps. And now we can calculate the head loss in pipe 3. Again, we are going to use HF is equal to KQ to the power of M equation. So we found K value, and based on these K values, we'll calculate each head loss value in pipe 3. And after that, to plot the data and to find the actual flow rate in each pipe, we need to create a new table. So if you remember from previous question, we were usually using Q here instead of head, but this time we have different flow rates for each pipe because they have different diameters. Instead of using flow rate, we are going to use head because it will be same for all of them. So here we need to use interpolation again. So we are going to calculate flow rates based on the heads. So for the first flow rate, which is in pipe 1, we are going to calculate the net flow rate for the pipe 1. And to do the interpolation, we are going to use this column and also this one. So for example, for the head for 180, we have 0 flow rate. Therefore, we are starting from 180. The main purpose for that, we are actually trying to create a common y-axis for all of these pipes. So if you go to the second one, instead of using 162.5, again, to create a common table for all of these pipes, we are reducing these values by 20 so that we are going to find all of the values for these heads only. So when we go here, we have 160, which is not available here. So that we need to interpolate between 180 and, between 162.5 and 140.7. So for example, the flow rate at 162.5 is 10, and flow rate in 140.7 is 15. So that for 160 feet, we have something between these two values. Since it is much closer to 10, we get something like 10.6. And we are following the same equation. For example, for 140, we don't have directly 140, but we have 140.7 and we have 110. So it should get some value between these two flow rates. And since it is very close to 140.7, it is now 15.1. So you can again use your calculator or online tools. And similarly for the second second pipe, we need to calculate flow rates. And for this case, let me use another color. This time we are using this column, which is the net head for pump 2. And also again, the flow rate. So since there is no flow rate until 110, we have blank values here. And since also we don't have 110 here, we are directly starting from 100. So for 100, which is between these two values, we will get something between 0 and 10. So we calculated 6.2. And we do everything same. And here we are stopping at 40 because we don't have 20 for these two pumps. So now we calculated net flow rates for pipe 2 and pipe 1. So the main idea here is we are using heads to calculate flow rates. Similar to pipe 1 and pipe 2. For pipe 3, this time we are using the head loss because, as you know, all of these values are related to each other. For example, for head loss, it is related to flow rate. And also for pump heads, they are also related to head loss and also the elevation. So that we can directly interpolate these values because actually when we say net pump head, it is also coming from the flow rate. So we shouldn't worry about the relationship. And for pipe 3, we don't have pump, but since we have head losses, we can use it to calculate flow rates. So similarly, we are going to use, let me use blue. We are going to use this table, this column with, again, flow rate. So for example, here we have 180. And for 180, let me find that. We have 48.3 CFS for pipe 3. So here, the 180 will be between these two values. So these two values are 40 and 50. So that 180 should be between 40 and 50. So interpolation gives 48.3. And for example, for 100, 100 is also here. It is between 30 and 40 CFS. So the interpolation gave 35.7. So repeating these calculations for all of these heads, we can get flow rates for pipe 3. And finally, we are going to have a Q system, which is the combination of QP1 and QP2. So basically, we directly wrote everything here because we don't have any QP2. But here we are summing all of the Q1 and Q2. And this is the Q system. And now we have calculated, we actually created the flow rate and head table. And to find the actual flow rate, as you remember, we need to find the intersections. We can skip to the table. So here we have 4 different curves. The first one is this blue line, which is the head loss, which we calculated here. The second one is this red curve, which is net HB2. It is coming from this table, this column. Another one is this dark blue, and it's coming from net HB1. And finally, we have Q system, which is shown with this yellow line. Sorry, actually, for this one and this one, we don't need to use this table. We are directly using the values here because we already interpolated. So based on these heads, we have these flow rates. So for example, for 180, we have something like 48.3. And for the second pipe, which will be this red curve here. So since it is starting with 100, it will have something like 6.2. And for example, for 40 head, we will have 20.8. So it will be around here. And finally, for this first pipe, for example, for 180, we have 0. So it is actually starting from here. And for example, for 100 feet, and we have something around here, which will be 21.3. Sorry for the confusion. We are just using this table to create this plot. And finally, we have Q system, which is the combination of these 2 pipes. So as you can see, at 180, it starts from 0. And at this point, it is 18.4, which is still same with pipe 1. But after that, we can see the impact of second pipe. So for example, for 100, it is 27.5. Okay, now we can calculate actual flow rates for each pipe, considering this table. So we will get the intersection here. For the pipe tree. So it is around 34 CFS. And this almost gives 90 feet. And similarly, for the same fit, we are going to calculate flow rate in pipe 1 and in pipe 2. So we have another intersection. And we have another one. So this makes 11.5 CFS. And for pipe 2, it is around 22.5 CFS. So we are reading CFS values, we are reading flow rate values from the same head of 90 feet, which is here. We did that because we need to find the intersection between the system curve and pump characteristics. And since we have a pump characteristics as parallel pumps, so we directly use this combined pump curve instead of these individual ones. So we needed to intersect the system curve with the pump curve. So this yellow is the combined net pump curve. And here, this blue line, which is the flow rate in pipe tree, it acts as the system curve, and their intersection is here. So since the head is 90 feet at this point, we were able to calculate the flow rate for pipe tree. And after that, using the same head, we calculated other flow rates. So also, as I mentioned at the beginning, Q1 plus Q2 was equal to Q3. So this was 34. Q1 is 22.5, and this is 11.5.